Hello, good morning, and welcome to the first lecture on our Robust Estimation and Controls course. This is going to be slightly different. So, because we're going to be recording most of the lectures, and what I'm hoping to do in this lecture is kind of give you an overview of the course and then talk about what we're going to be doing and then kind of cover some of the basics. So the format obviously is going to be recorded lectures here. And so without further ado, let's go to the class. So this is going to be our first week. So the way I envision the lecture going is that I would upload these blank notes, or you can kind of like follow through the lecture, or and you can. I would essentially give in most of the like the key features, kind of like a blank template notes, and that you would fill in. I don't actually plan to upload the completed notes, so you would need to actually follow the lecture and then fill in the notes and then use that for your reference. So the first week, our learning objective is going to cover the introduction of the course, and then we will go over review of some of the topics in control systems. So these would be something you would have already learned in your prerequisite. Nonetheless, these are going to be important concepts that we're going to be using here, and it also allows us to kind of like catch up and on what's going on here. So what is our course overview? So generally, if you look at real world measurements, you're going to have some noise that's creeping in. So for instance, the mic that I'm using to record is going to pick up some stray noise. So for instance, there is a vent in my room, so it's going to pick up those noise, and maybe there is other kind of noise. So those would be kind of like a whoosh kind of noise that comes in from the vent. There are other kind of disturbances that could come in. There could be somebody knocking on my door. There could be something else that's happening. Maybe there's kind of an earthquake or some sort, and then that's going to disturb, and then that's going to cause a noise because the microphone boom is going to pick up those noise. And as designers, we want to improve the reliability. So before we actually go into the noise, so let's look at a slightly simpler example. For instance, assume I have this kind of a measurement. So I have three measurements of my length. So I have one which is 10.1, the other one is 10, and then this is 10.2. So the idea would be, so you have like either three people measuring a particular length with your ruler, or you're taking three consecutive measurements. So the question then becomes, what would be your best estimate of the length? So this is a fairly simple example. So what you would do is you'll say, okay, hey, what I'm going to do is just take the average of these lengths. And so my best estimate would be to basically do the average, which is 10.1, 10, and 10.2. The average is 10.1. So this is fairly straightforward. This is what we call as a static measurement. So something that doesn't change with time. So you can take consecutive measurements and you wouldn't be in too much of a trouble. Let's take an example of a dynamic system whose parameter keeps changing. Now the question becomes, how would I do the averaging? So obviously, if I average and then take three consecutive measurements, my system itself might have changed in that time, which would be not that great to average. The other option would be to make multiple consecutive measurements, which would require more number of sensors. For instance, if you wanted three measurements, you'd have three sensors. For instance, imagine you're driving in the car and you needed to have three speedometers, and then at each measurement you look at all three of those and then take the average, which is not that great for the car, but they do end up doing something similar when you need very high reliability. For instance, if you look at like the instrument clusters in aeroplanes, they actually have like three different pitot tubes, and then there's one for the pilot, there's one for the pilot or the captain, and then there's one for the co-pilot, and then there's a third one which is acts as a redundancy. So if all three of them kind of like match up, then you can be reasonably sure that your the measurement is correct. So anyway, coming back, for most systems, this is not very ideal. So this would actually increase system complexity, and then this makes it difficult. So the question then becomes, is there any other way of doing a redundant sensor? So rather than just use a measurement, what we do is look at the model of the system, which can be used to predict the response of the system, and then that kind of acts as a redundant sensor, which we can then do some intelligent combinations, and then we would um, um, essentially use that as a redundant sensor and get around this problem. So now this prediction can serve as the virtual sensor. So the other thing that we want to look at is not all measurements are the same. So what do I mean by that is some measurements are more reliable than the other. So for instance, in our previous measurements, so if say measurements 1 and 3 were taken by a cheap sensor, or you had and with the reliability of 1 unit, so we'll kind of talk about what these reliability measures will be at a later point. And then, so for instance, I also tell you that the second measurement was taken with the instrument with the reliability of 3. So now the question becomes, how would I use this new information where I want to maybe use a lesser weight for my first and the third measurement and then provide more weight for my second measurement? So obviously you don't want to just completely ignore the first and third measurements because you have like two of them. And then the second measurement is kind of more reliable, so you don't, but there is still some uncertainty. So if I told you that the second measurement is 100% reliable, there's no issues at all, then you probably just like throw away the first and third measurement. In this case, you can't quite do that either. So obviously what you would do in this case is kind of do a weighted mean. So weightage would be based on your reliability, right? So what I could do is essentially do a weighted mean calculation over here. So the weights would be the reliability of the sensors. So we multiply 10.1 by 1, 10 by 3 because it has 3 times or 3 units of measurement, and then 10.2 by 1. And obviously, if you just added those up, that wouldn't be great. So you need to divide by the total weight. And then, so if we did that, we can calculate what this weight would be. So in this case, you can kind of pause the video and then try to calculate this value and enter it in the system. So this case is going to be 10.06, which you notice is much closer to our 10. Again, you can't really distinguish between this method and the previous method unless I tell you what the actual reliability on the sensor is. So let's go back and then let's see how we can do this in a similar way. So what we need to do is kind of calculate the, we need to come up with some measure for the reliability of the system. So what we do is we use the size of the noise and the distribution as a measure of reliability. So the entire course would kind of focus on kind of doing this, where we would look at essentially figuring out how we would kind of come up with this measure. So this is going to be the course overview. So the objective of the course is obviously to cover Kalman filtering. So if you're doing this in MSE, so your three prerequisites are going to be linear system, system modeling and control and feedback. So this is going to be given, provided to you. The learning outcome is going to be kind of like recall concepts and then mainly focus on Kalman filtering over here. So this is the policy on the course assignments and so on. So we have the grade cutoffs that we're going to be following for this course. So we take plagiarism very seriously. So make sure you understand the policy. So any issues will be reported to the department chair. And then this will essentially, based on the seriousness, you would lose either like just lose credits for that particular work, or it might be more serious and then maybe more consequential disciplinary action. This is the tentative schedule that we're planning to follow. So we'll start with reviewing some important concepts and kind of using MATLAB control system toolbox. We'll cover a little bit about state space control, talk about vectors, matrices, and controls problem. We will go into digital or discrete time control systems, where we talk about the concept of sampling and sampling theorem. In week 5, we'll cover probability, which is where all of the noise and the Gaussian process come in. We'll follow this with random variables. Week 7 would be midterm, and where we start covering filtering. Week 8 would be least square estimation. Week 9 would be Kalman filtering. I know it's kind of towards the end. but we need to actually build up all of the basics before we can actually get into Kalman filtering. So 9 would be Kalman filtering. So it will focus mostly on discrete time system. And then we look at this generalization of the Kalman filtering and application to continuous time system week 10. Week 11, we'll start looking at nonlinear system and then an H infinity controller and so on. So this is kind of the overview of the that we're going to follow. All right. So now we're coming back and then looking at some of the basic concepts over here. So the very first concept that we'd like to look at is the concept of open versus closed loop control. So this is kind of just a background. So conceptually what we're doing is we typically have a system over here. So we call this a plant. And then this is something we want to control. And the controller is something we want to design. So typically what will happen is for the plant, you would have an input, which is denoted by U, and an output, and then you have a reference that you want the plant to track. So essentially in the closed loop control, it's typically less expensive. Notice that there is no feedback over here, so we're not actually measuring the system output to do like an intelligent control. So essentially we kind of like guess, hopefully we have a good idea of what the plant would do, and then based on that, we would set the reference. So this is for systems without dynamics. U could probably be easier to calculate. U here is input, and then you can kind of do this fairly easily to actually run the system. The problem mainly comes if you have a disturbance, and the question is how do you deal with this? Challenges arise because of the unknown disturbance, and then you can also have a measurement noise. So obviously the measurement noise isn't too much of a concern when you have an open loop system, because you're not really using or you're not doing anything with the actual measurement. So the question then becomes, what is the disadvantage over here? It's firstly this disturbance over here. The second issue is if there is some kind of an uncertainty in the plant model. So let's look at a similar thing, but now we're going to look at the closed loop control. So again, we have the reference. Just hang on, don't fill this as yet. So we have the disturbance over here. And then what we're going to do is we still have the noise over here. Rather than directly filling in the reference, what we do is we're going to kind of like use this feedback over here, where we have the reference going into this circle. The circle here represents an additive term. So you have the reference coming in, and then you have the measurement with the noise coming in over here. So the difference between the two would be your tracking error, and this gets fed to the controller, and the controller uses this tracking error information to calculate the input to the plant, and then that's that. So essentially what we're doing is we're replacing the original reference with the tracking error over here. Since the controller actually measures the system output, this is where the disturbance comes in. So essentially, if you have a very high noise over here, so notice that the noise gets fed back into the controller. So if you have very high noise, the controller, whatever it's doing, it could potentially amplify the disturbance, the noise over here, and then the disturbance also gets fed. So essentially, we want to do some intelligent design over here to minimize the effect of the noise. So the question then becomes, what can we do? So then what we do is we, instead of directly feeding in the measurement, we apply some kind of a filtering and then use that in our controller. All right, moving on to the next topic and moving the camera a little bit down. So we are going to be looking at doing system modeling. So the idea, hopefully, is you've done this all before, and this is just going to be like a quick breeze. Just make sure everybody is comfortable, make sure you're on the same page. The reason we're doing this is system modeling is going to be useful when you want to actually construct the model that would then be used in your Kalman filter. So we want to make sure everybody's on the same page. So the first model we're going to look at is going to be a simple spring mass damper system. These are the notations we're going to be using, F is for force, and then we're going to use the subscripts M for mass, K for spring, and then B for the damper. It's the traditional letters that are used. And then we would use y for the position, v for the velocity, and a for the acceleration. Right, so now, so we know that the velocity is going to be the rate of change of position. So that's going to be v equal to y dot. And then acceleration is similarly the rate of change of velocity. So this is going to be a equal to y double dot, v dot or a double dot. So the next thing is we're going to look at the mass over here, which is just a little block with the letter m to denote the mass. So the dynamics is given by the Newton's second law. What that means is if you're going to be applying a force F sub m on the mass, we can calculate the acceleration using Newton's second law. So we apply this force, and the force should be equal to mass times the acceleration, or it's going to be m y double dot. Right? This is fairly well known. So we can do similar thing. We are looking at a spring or for the case of dynamics, we're going to assume that the spring is massless. So this is an approximation that we do. We can model the mass of the spring. It will be a distributed mass. We can do it in more advanced modeling. It just makes it more complicated. But for a simple case, we'd assume that the spring mass is so small that you would neglect it in the calculation. So the spring constant is K. So what that means is if I'm stretching the spring a little bit, it's going to apply a force and then try to pull back. So that's given by Fk. That's going to be, and then we similarly apply a mass damper here. The force is going to be K times Y. And then similarly, if you look at the damper, which again is also assumed to be massless, the force is going to be the damping force times the velocity. So the point to note is these are going to be opposing forces. So if you want it to be pedantic, you would, or actually more mathematically accurate, you can use a negative sign and then just call it all happening in the same direction. So if we assemble the spring mass damper together as such, we've already calculated these values. So we can write this down. So Fk is K times Y, Fb is B times Y double dot. And here is where things get a little bit interesting. So if I'm applying a force F here, that basically means I'm going to be applying a force here, but the K, the spring, and the damper are going to be applying an opposite force in this direction. So we're going to assume all the directions are positive going left to right. So that basically means we here need to substitute the net force, which is going to be this F, minus whatever force is being applied over here. So that basically means I'm going to have F minus F sub K minus F sub B, and we equate that to the mass over here. That gives us MA, which comes from here, is equal to the force, which is going to be F minus KY minus BV. Or we can rearrange the term. So we move all of this stuff to the left. We substitute y double dot is, or rather, the acceleration is y double dot, and then the velocity is y dot. All right, moving on. So we look at the modeling of an LCR circuit. This is going to be modeling of an electrical component. So here, the modeling is going to be fairly similar to what we did before, but the concepts that we're going to be using is the charge, which is given by Q, which is the integral of current I, being the current over here that is flowing through the circuit, the V capacitance, which is the voltage across the capacitance that will be measured over here, is given by 1 over C integral of I dt. And if you substitute it for integral for I dt as Q, you get this as Q over C. And then the VR is going to be I times R, which is R being the resistance times Q dot. And then VL is L di by dt, which becomes LQ double dot. So this would be a good time for you to take a break and then try to work it out yourself and then see if the things matches up. Okay, so now if we sum up the voltage, we need to ensure that if we go apply a voltage V in over here, so you're going to have some drop over the resistance and then some drop over the inductance, and then there's going to be some drop over this capacitance, and then when you come back, you need to reach the 0, right? So there's going to be an increase in voltage, and then there's going to be a decrease. So essentially, we are going to have that the voltage, positive voltage over here, should be equal to sum of all the negative voltage. So if we do that, we can actually calculate, we set the output V, or rather Y equal to V out, which is Q by C, and we do all the calculations out of Q. So since the voltage sum should be equal to U, so we have V sub L plus VR plus VC should be equal to U. And if we do the calculation further, substituting in for VL, VR, and VC, we find that LQ double dot plus RQ dot plus Q over C should be equal to U. So what we can then do is substitute for our Y, where Q over C is Y from here. So if we substitute Q over C as Y, and then what you're going to have is Q dot is going to be C Y dot, and then Q double dot is going to be C Y dot, double dots, and then we get this term over here. So this looks fairly similar to the second order equation that we had for our spring mass damper, just that instead of mass we have LC over here, and then instead of the damper we have the RC, and then there is nothing that's multiplying K over here. So there's some variation, but the dynamics itself is going to be fairly similar. So that's what we note over here. So the next concept we're going to be looking at is the Laplace transformation. So Laplace transformation is a special transformation that converts a signal from the time domain, which is our normal operating domain, and then we convert that into the Laplace domain, which is also known as the frequency domain. So the preliminary is we need to ensure that the signal itself is kind of limited in energy. So we basically say that the integral f of t e to the minus sigma t, the absolute value of that should be less than infinity. So if that function satisfies, if a function f of t satisfies this equation, then we can say that the Laplace transformation exists. And then we say Laplace of f of t, which is given or symbolically written as the script L times of f of t, is defined equal to, so this term over here, is used for defined equal to. So that's defined equal to integral 0 to infinity. Here it's going to be little f of t times e to the minus s t times dt. So here s is defined as the Laplace operator, and s is typically a complex number written as sigma plus j times omega. J is the imaginary number because we use current in electrical and control systems. We use the letter j, and then we typically never calculate this by hand. So we're going to look at some interesting or useful properties of the Laplace and kind of give a hint of where this came from or why this was important. So if you look at the Laplace of k times f of t, so essentially k is a scalar factor that is equal to k times f of s. So if you look at the sum or the difference, so the Laplace of f1 of t plus f2 of t would be equal to f1 of s plus f2 of s. If you look at the differentiation, the d over dt of f of t would be equal to s times f of s. So notice that it becomes multiplication by s, and then minus f of 0, little f of 0, which denotes the initial value of little f. So again, the little f's denote functions in the time domain, and then capital F denotes the function in the Laplace domain. And so we can extend this to like a higher order differentiation. So d to the n f little f of t divided by d t to the n is given by s to the n times capital F of s. So this is the only term that involves, so this first term is the only one that has capital F. So rest of it on following that are going to be the derivatives of little f of t. So we basically have s to the n f of s minus s to the n minus 1 f of 0. So this is the actual value at time equal to 0 minus s to the n minus 2 times f of 1 So this basically is df over dt. And so we keep going on and on. And so this is basically f to the n. So this is basically short form for writing d to the n minus 1 f divided by dt to the n. And so we keep going, and we can kind of write the derivative like that. So we can similarly do the integral. So the integral from 0 to t f of tau d tau. So the reason we use tau here is because we want to differentiate, the t appears in the integral, so we want to differentiate the letters. So we write it as f of tau d tau. So this becomes 1 over s f of s. So the point to note here is that the Laplace transformation has the advantage of converting derivative or differentiation to multiplication by s, and similarly if you have the integration, so that becomes a division by s. So this is fairly powerful, particularly when before the time when you actually had like computers to do numerical simulations, you could have still done the calculation, and this is where we have a lot of the theories regarding the stability and all of the analysis of our system is based on this Laplace transformation over here. So the next important property is the time shift. So if you look at this function over here, so the Laplace or f of t minus capital T times u of t minus capital T. So what we're essentially saying is we are looking at the signal starting at time capital T. So if we look at that, so what is u sub s? So that's actually a unit step. So if you wanted to plot the step and then you have the time here, so this is how the step actually looks. So if you look at the Laplace of the time shift, so that is given by e to the minus capital T times s times f of s. The other two properties that we have is the initial and the final value theorem. Initial value of little f of t is given by limit t going to 0 of f of t. So that's given by limit s tending to infinity, s times f of s. And then similarly, we have a final value theorem, which is the value of f of t as t goes to infinity. So that's given by limit s tending to 0, s times f of s. So here's a simple example. So we would like to calculate the initial and then final value of 1 plus 1 over s plus 1. So you can pause this video and then upload the results. So the initial value is given by, going from the previous slide, is given by limit s tending to infinity, s times f of s. So we substitute that value, so it becomes limit s tending to infinity, s over s plus 1. So the problem here is if we substitute infinity and infinity, so we'd actually have infinity over infinity, which is not defined. So we need to do something different. So what we do is multiply and divide, or rather divide the numerator and the denominator by s. So that gives us 1 over 1 plus 1 over s. And then if you can take the limit as s tending to infinity, this term over here becomes 0. So this becomes 1 over 1. And so our initial value is 1. Similarly, if you wanted to calculate the final value, so that becomes limit s tending to 0, s times f of s. So here it becomes s tending to 0, s over s plus 1. So we don't want to do the same trick over here because 1 over s would give we can directly substitute for 0 and there shouldn't be any issues. So if we do that, we get 0 by 0 plus 1, which basically becomes 0. So now we're going to look at some of the applications of the Laplace transformation. So recall the spring mass damper equation that we had, which was m y double dot plus b y dot plus k y is equal to little f of s, so f of t. So what I've actually done is replaced the input u with f. So we're also given that the y at time equal to 0 and then y dot at time equal to 0 is 0. So we will define the Laplace of these variables. Particularly, we start with the Laplace of y. So we'll define capital Y of S as the Laplace of y of t. Similarly, we'll define f of S as the Laplace of little f. So when you do that, then we need to next calculate the Laplace of y dot and y double dot. So the Laplace of y dot, if you recall, is s times y minus y of 0. Because y of 0 is 0, this basically just gives us s of y, s of capital Y, s times capital Y, excuse me. And if you do Laplace of y double dot, this becomes s squared capital Y minus s y of 0, little y of 0, minus s to the 0, y dot of 0. So s to the so all of these values, little y of 0 and y dot of 0 is 0. So that basically means Laplace of y double dot just becomes s squared times y. So the other property that we use is because the sum of the Laplace is equal to the Laplace of the sum. So we can basically just simply substitute for y dot. If you're basically doing the Laplace of this whole equation, we can just take the Laplace of the individual terms and then add them up. So that basically means we get m, and then we substitute for y double dot, the Laplace of y double dot. This becomes s squared times y plus b s times capital Y plus k times y. And then we can just rearrange the terms, and we basically get capital Y, so divided by f. So we just take all of these terms is 1 divided by m s squared plus bs plus k. This is called the transfer function and is typically denoted by the letter g. All right. So next we're going to look at basic usage in MATLAB. So we're going to create an impulse response, a step response, Bode plot, and Nyquist plot of the transfer function 16 divided by s squared plus 10s plus 16. So again, if you're doing it manually, it's a lot more work. We're going to use the power of MATLAB here. So the function that we're going to use is known as TF, or transfer function, to actually create this transfer function. So I've already opened MATLAB over here. So if you wanted to figure out what things are, so we're going to go and then type help and then TF, and then it tells you all of the help that is available for this particular function. In particular, how is it that you're going to create this function, and then how would you use it, and so on. And it also gives an example. So if we scroll up over here, so it says one of the ways you would create it is you have TF and then you have numerator, comma, denominator. You can also create it, give sampling time. You're creating a discrete time, so it's just a signal. We're going to ignore it. We can also create it, create S is TF of S, and then do it in different ways. So we're going to look at doing something, creating a numerator and denominator polynomial. So the way numerator and denominator polynomial are going to be is that they're going to be in decreasing powers of S. So let's create that first. So we'll create the numerator and denominator, and then use that to create our polynomial. So the first thing we're going to do is we're going to store the different powers of the numerator and the denominator in two separate variables. So in MATLAB prompt, we're going to say numerator is 16 and denominator is it's 1 times s to the 2. So we're going to put 1, and then 10 times s to the 1, and then 16 times s. So these are the values we're going to be storing. Again, so these are going to be the, so we just grab the coefficients from each power of s and then put it in here. So let's do that in MATLAB. So CLC, so we go numerator, (16). So notice that it prints the stuff on the screen, which I don't like too much. So what I'm going to do is make it without printing. So we're going to go add the semicolon. So this becomes denominator is 1, 10, 16. So now it doesn't print anything. And then what I'm going to do is create a transfer function. We'll call that G. So this is going to be G is TF of numerator, comma, denominator. So this creates our transfer function. So then we go back and see if we can do all of these plots. So next we are going to create use transfer function to create the transfer function. So next we just use impulse of G, step of G, Bode of G, and anything else that you want. and then create those corresponding plots. So let's do that. So we're going to go impulse of G. So this is the impulse response. So here we have the impulse response, we have the time, and then the amplitude. So the impulse response is kind of like giving a kick to the system. So we can next do the step response of the system. So instead of impulse, we try step, and then we hit enter, and then you're going to get the step response. So that's the figure over here. And we can similarly do the Bode plot of the system. And so we do the Bode plot. So this gives the frequency here, and then this is the Bode magnitude and the Bode phase over here. And similarly, we can also do the Nyquist of that particular system. And so we do the Nyquist, and then it plots it in the same figure. And so this is the Nyquist plot. So this is the stability point for the Nyquist, and then this gives the Nyquist plots itself. So just this once, I'm going to also show you an equivalent software, which is an open source software called Octave. So we're going to pull that up over here. So you can download it. If you just search for Octave, it'll tell you how to get the software. And so what we're going to do is I've copied the steps already. So I'm going to just do the impulse alone. So I'm going to copy and then paste this here. And then it opens up a figure, and then notice that the impulse response is fairly similar. Let's do the Nyquist and then see how it looks. And so this is the Nyquist plot. So this looks fairly, so it's doing the same calculation, so it should look fairly similar as well. So again, so this is an open source software. It's called Octave. It usually has most of the functionality of MATLAB, but it lacks some of the advanced functionality. So this is actually useful if you don't have an access to MATLAB, and then you can kind of do most of the calculations in Octave as well. All right. So the next concept you're going to be looking at is known as the zeros and poles of a transfer function or a system. So we're going to use MATLAB to plot the system 10 times s minus 1 divided by s plus 2 plus times s plus 5 to the input e to the t for 10 seconds. So we are going to look at the transfer function over here. So notice that we have basically written it as, so you can write a transfer function as a polynomial, but what we have done here is we have actually factorized the polynomial. So the numerator is factorized as s minus 1, and the denominator is s plus 2 times s plus 5. So if you could potentially multiply this out, and then you would have essentially the transfer function we had before. So what we actually do here is the roots or the solution to the numerator polynomial known as the poles of the system. Excuse me. The solutions to the denominator are known as the poles of the system. And then the solution to the numerator is known as the zeros of the system. So one way to do this is to kind of like multiply the numerator and denominator, and then use the transfer function designation we had before. But we're now going to try to do the system in or represent the system in MATLAB in a slightly different way. Since we know the zeros and poles, we're going to use what's known as the zeros and poles representation within MATLAB. So the system actually has poles at -2 and -5. So what do I mean by that is if I substitute s equal to -2 in the denominator, so this term becomes 0. So that's a solution to this equation. And similarly, if I substitute -5, it becomes 0. So this is fairly obvious in this format. Similarly, for the numerator, if I substitute s equal to +1, this term becomes 0. So that's the 0 of the system. And then it has a gain of 10 over here. So what we do is we use in MATLAB a function called ZPK, which is short form for zero, poles, and K is for gain. and then we'll do it in this format over here. So here we have G, again for the system is ZPK of 1, which is the 0, minus 2, comma minus 5, which are the poles, and then 10 is the gain. So let's do that in MATLAB. So we're going to open up MATLAB over here, and then I cleared the screen already, and then we're going to type in this, and then we have, since I didn't put the semicolon, so it's showing me the system, and notice that it's actually exactly equal to the system. Right? So just for the fun of it, let's try to do a step of the system. So we go step G comma 10, so this gives a step for the first 10 seconds. So we do that in MATLAB. So it creates in the same figure. So this is the step response. So it goes on this side and then on the other side. It seems stable enough. All right. So next, since we're going to do the plot, so we need to generate our input for 0 to 10 seconds. So we're going to kind of create the input in that format. So let's so what we're going to do is define time going from 0 to 10 seconds. So we're going to go t is 0 in increments of 0.1 second, 0.01 seconds, and then we go from 0 to 10. This is the format you create in array in MATLAB, and then we can create our input, which is e to the 1 times t, and we can actually do that in MATLAB now. So we create these two in MATLAB. So we have a t and the u. So the next thing is we are going to use is a function called LSIM, which stands for linear system simulation, and the function actually takes the system u and t. So again, we can look at the help for this function. So we do help LSIM. It actually accepts different format. So you can scroll up. So you basically do system ut, and then if you actually do y equal to LSIM of system ut, it stores that into the variable y. So we're going to do CLC, which is clear screen in MATLAB. So let's do that. And then if you do this, it creates a linear system, and then we're going to plot that. So we're going to copy these. So I'm going to type in these two commands in MATLAB over here. And so if the simulation is done, so you notice that there's a plot, and then notice that it actually goes to 0. So just to make sure we're not doing anything like we're not in error, let's actually try to plot the input of the system. So if you do that, and then notice that the input actually exponentially increases, but then the output of the system doesn't seem to reflect what's happening in the input. So this is kind of strange. So we'll take a closer look at what's actually happening. So this is the response that we had. So we can do some analysis in the Laplace domain. So if we look at the Laplace, e to the minus alpha t is 1 over s plus alpha. So e to the plus alpha t is going to be 1 over s minus alpha. So in this case, our value of alpha is essentially minus 1. And so we get u of u is 1 over s. So essentially, if you look at the system, so the numerator essentially cancels out the denominator, and so this actually becomes 0. So this is the reason this is called the 0 of the system. The numerator or the roots of the numerator polynomial are called 0 because it kind of cancels out the input or zeros the input. So let's take a more general system. So if you have a numerator by denominator polynomial, and then you can write it in this format. So we have z s plus z1 times s plus z2, so on and so forth, up to zm, divided by s plus p1 plus times s plus p2, so on, times to pn. So where z's would be the zeros and p's would be the poles. And then if you take the input in this format, s plus z sub u1, and so on and so forth, So what will be the system? The response of the system, if you recall, is going to be G times U, and so this is the product that we get. So essentially, we have the potential for terms in here, canceling out terms in here, and so on and so forth. So now we're going to do some exercise to figure out, or at least kind of appreciate the importance of Laplace transformation. So what we're going to do is we are given this transfer function of the system over here, and then we're going to calculate the response to a step input, which is u equal to 1, as well as u, or the input is 1 plus e to the minus t. Since the g is actually y over s, so what actually happens is y is g times u. So essentially all of this just becomes like multiplication in the Laplace domain. So this is s plus 1 divided by s squared plus 5s plus 6 times u of s. What we need to do is determine the Laplace of the input, and then if we can do that, we can substitute this value. So the Laplace of the input is 1 over s. How do I know that? Is from the Laplace table over here. So if we go all the way up, so we have u of t, which is just an input value, unit step. The Laplace is 1 over s, and so that's what we substitute over here. So you would have this table in back of Professor Goldenragi's book. So we're going to use that as our reference. So once you have that, so we're going to calculate the response of the system. So it basically becomes just g times 1 over s. So if we go back, we have two options over here, right? So we can multiply the denominator out where I'll get cubic terms and then try to figure out what the inverse Laplace is going to be. But then if you go to the Laplace table, it only has terms up to s squared. Right, so this would be a problem. So what we need to do is kind of go in the other way, is to actually figure out some way of transforming this equation into a combination of lower powers of s in the denominator. So before we do that, so what we need to do is calculate the roots of the system and then use that information just a bit. So what we do is first solve for the denominator over here. So it's s squared plus 5s plus 6. So we use the method of, so we solve, so this becomes minus 5 plus or minus square root of 5 squared minus 4 times 1 times 6 divided by 2 times 1. And then if we substitute, we get s is minus 2 and minus 3. So hence, the denominator can be written as s plus 2 times s plus 3, or we multiply this out. So the equation y of s should be s times s plus 2 times s plus 3 the denominator, and then s plus 1. Right? So this again doesn't solve because the Laplace transform doesn't really have multiplications either. So the next thing is we need to figure out how to convert this into a sum of Laplace, which we know how to solve. So this is where the method of partial fraction comes. So we are, for more details, you can look at the section 2.5 in Dr. Goldenragi's book. So the basic idea is, so we do the Laplace transform, and inverse Laplace transforms are additive. We have Laplace transform for simple terms like 1 over s, 1 over s plus a, and so on. Hence, we'll convert our complicated fraction into sum of simpler terms. The idea is we are going to find some constants k so that our equation here is identically equal to, this three lines means identically equal to, which means it's true for every value of s. So it's going to be the sum of these three values. So the reason we get this is if we multiply all the three denominators, we end up with the denominator on the left hand side. So that's the only way. And so we have like additional terms. If I put k4 by s plus 4, because I wouldn't have anything in the denominator, so those terms would be 0. So this is how we do. So typically we factor the denominator, and then we actually have as many terms as the number of products over here. So once we have that, so we need to equate this. So we're going to multiply the terms and then equate the powers of s. So how do we do that? So we're going to rewrite the right hand side. So we multiply this. So this becomes k1 times s plus 2 times s plus 3, which is going to be these two. And then k2 times s plus 3. and then K3 times S times S plus 2. Essentially what happens is whatever is there at the denominator, that term would be missing from this product over here. Right? So once we do that, so we're going to compare the two terms. So we're going to select the term so that this term over here should be identically equal to the previous term over here. So how do we do that? So essentially we are going to just compare the coefficients of different terms. So here if we multiply this out, so we're going to get different powers here. So let's look at terms that will contain s squared. So you're going to have k1, and then this is going to be k2 and k3. So we're going to have powers of s squared is going to be k1 plus k2 plus k3. And then on the right hand side, since there is no s squared, this sum should be 0. We look at the power of s, so we multiply that out. So we get s times 3 plus 2, and then we multiply, we get 5 k1 plus 3 k2 plus 2 k3. And then for the constant term, we get all of the constants. So 2 times 3 is 6. And then we don't get any constant term from here. And then we don't get any constant term from here. So we have to solve these equations. So we have three unknowns, k1, k2, and k3. And then we have three equations, and we can solve it. So this is not particularly difficult. So what you can actually do is use the last equation over here to solve for k1, which is going to be 1 over 6. We can eliminate k1, and then we have two equations, and then we solve for k2 and k3. So you can pause and then calculate these values. And then once we do that, we can substitute the values. So we get k1 is 1 over 6, and then k2 is 0.5, and k3 is 0.6667. So these are rounded off. And so what do we do next is, because we know the inverse Laplace of s plus 2 and s plus 3, if we calculate the inverse Laplace of y, we get the sum of those terms. So we get y is 1 over 6 or 0.1667 plus 0.5 e to the minus 2t and minus this and so on. So again, how do we get this? Again, we look at the Laplace table. So the inverse of 1 over s is just a step. So the inverse of s plus alpha is e to the minus alpha t. And so we can just substitute those values over here. And so just to look at this, if you look at taking t to infinity over here, these two terms disappear, and then we get 0.1667. And just for the fun of it, you can put in other values. So essentially, we'll expect a short overshoot. So the other examples are like for you guys to try it out yourself and then see something interesting that happens. And then you're going to write a comment on the video or submit it as the response to the video. All right. Finally, what we're going to do is look at the effects of the poles. So we're going to imagine we have a system which we have written on the form k divided by s plus alpha times s plus alpha 2, alpha 3, and so on and so forth. So let's see what actually happens if all the poles are negative. So essentially, if all of the poles are negative, so what happens is, since the response is going to be y is beta times, so essentially you'll have some constant using our partial, the partial fraction analysis that we did. So we would actually have an equation of this form for the response of the system. So if all the poles are negative, so all of these terms are exponentially decaying. So just a quick caveat, so you could potentially change these locations of the pole with feedback, but for now, you're going to ignore the effect of the feedback and then see what actually happens. So now, if all the poles are actually negative, the system response eventually goes to 0. If any one of these is actually positive, the system response actually blows up. So essentially, you can say if all the poles are negative, the system is stable. If one of it is actually positive, then the system response goes to infinity, or the system blows up. So the positiveness of the pole actually indicates system instability. So this basically concludes our quick introduction on the chapter and the quick introduction to, or quick recap of the concepts in control system. And then in the next video, we'll start looking at more interesting stuff in the state space domain. Thank you for watching and have a great day.